Section 3.1 is called Extrema on an interval. So all of Chapter 3, what we're going to do is we're going to take what we did in Chapter 2, which was derivatives, right? And we're going to see different applications of them. Some of them are going to start very, just like a graphical application, but then we're going to involve into some more like concrete applications that are more like real world kind of stuff with that information. And we've done a little bit with that already in related rates back in section 2.6 where we saw an application of derivatives. This is going to feel a little different than that. The benefit to what you see happening in chapter 3 is that the derivatives are going to be much cleaner and easier to work with. They're not going to be crazy. So that part's going to be nice. Also, as a reminder, if you have not already finished your gateway, you need to be coming in to do that. And that's a lot of you at this point to retake that test. You can retake it once a day until we get to next week, a fall break like that Wednesday. So you still have plenty of opportunities, but please don't wait until next Wednesday to do it or it's probably not going to work out so well. So you come in, you retake it. If I have the ability, I don't have too many students in my office or whatever, I'm happy to grade it for you while you wait. If not, I'll grade it later in the day and then just send you an email and let you know how you did, okay? All right, so extrema on an interval. So let's talk first about what extrema means. If f is a function defined on an interval I containing the point c, we would call f of c the minimum on the interval if it's smaller than everything in the interval. We would call f of c the maximum on the interval if it's larger than everything in the interval. The maximum and minimum values are called extreme values or extrema of the function on the interval. We also sometimes will hear the language used absolute maximum or absolute minimum or global maximum or global minimum. Your book tends to use the absolute words, not the global words, but they're mentioned in there. So in terms of a picture, if we have something like this, I didn't mean for it to quite go like that. Let's go with that. There's two different locations, generally speaking, where you could have maximum or minimum occur. One place that could happen is it could be on the endpoints. So these endpoints are sort of like options of places where we might have maximum and minimum values. The other option of where a maximum or minimum value is going to occur, potentially occur, would be at the valleys or the peaks of a function. So this one would be a valley, and we would have this location. Okay, so those are the different portions of the graph that we're looking for. And notice it actually talks about the interval I, and it's going to be a closed interval. It's going to start somewhere, it's going to stop somewhere. So we're not looking at the whole number line when we're talking about this particular concept. We will look at that later on a little different concept. But right now we're looking at a closed interval. It starts at 1, it ends in 10, or whatever the values are. So we have endpoints that we actually consider as possible options. So far, so good? So these are the points that we have to test. We'll call them test points often. And we can't just say, oh, well, I already kind of looked at the graph and I know that the endpoints aren't viable. That may be true, but you're still going to have to show me that that's what you did so that you know that they're not actually the endpoints. The endpoints are not giving you the maximum minimum value. So the extreme value theorem actually says that when the interval is closed, that's what I was talking about here, then there will always be a maximum and a minimum value. And I kind of glossed over this, but it is important. It needs to be a continuous function, no jumps or holes in the graph, of course, for that to work. So there's always going to be at least one place where there's a maximum and one place where there's a minimum. When we have those places where it has these curves, right, these peaks and these valleys, those are places where another type of extrema occurs. They're called relative extrema. They're sometimes called local extrema. So if there's an open interval containing C, on which C is the maximum or minimum value, you can say that F has a relative maximum or minimum at C, F of C. Now I always like to use an example from a point in our lives when my husband and I were youth pastors. He was a youth pastor, I was just his wife, but you know how that works. But anyway, we were youth pastoring up in Ohio, and my mom came to visit us, and she was like, oh my word, she felt so very short, okay? And it was very interesting because, so I'm 5'4"-ish. I'm probably shrinking at this point. I don't know. But I'm about 5'4", okay? And if you were to ask my mother, at least prior to that incident, she would have told you that I was tall. She would have told you that I was tall. And the reason she would have said that is because I was the tallest woman in my family. No joke. So my mom's about 5'2", her mom's about 5'1", my sister's about 5'2". I have a sister-in-law who's just barely 5 foot. Like, we have a lot of short women in our family, so in her mind, I was tall, okay? Because it's all relative, right? It depends on the comparisons that you're making. If I'm with my husband's family, I'm the shortest female in the family. There's a couple others who are about the same height as me. But I have a sister-in-law who's 5'8". For a portion of time, I had a sister-in-law who was like 5'11". She's not married to my brother-in-law anymore. That's why I say that. But I'm short. My mother-in-law's 5'5". I'm barely shorter than her, but I'm shorter. So this happened. My mother came to Ohio, and every teenager in our youth group was taller than me. Every single one. All of them. It's crazy, right? At least it was. I didn't feel like I was super short until I was with them, and then I really felt short. Okay, so it's all about context. We have some sort of ideas of what short and tall mean, but it depends on the context that you're talking about. When I stand up in front of you, I feel like I'm kind of in charge, and I'm taller than you, and then 3/4 of you stand up and you're taller than me, and I feel a little intimidated, especially for the men who are taller than me. I feel a little intimidated. You guys are tall, right? But it's all about what you're comparing it to, and that's the whole idea about a relative extrema. This location right here is a relative extrema because in the nearby locations, it's the smallest value. But let's say that this function continued, and the interval didn't really end here, but we actually continued down here. And if you compared it to everything on the graph, it's not the smallest value on the graph, not even close, right? But in a local area, in a confined location, it is. And that's what we mean by a relative extreme point. So our values that we're going to be looking at, where we have these locations, where we have these peaks and these valleys, are going to be called critical numbers. So critical numbers are defined as locations, and this is a typo on here, where the derivative is equal to 0. Okay, those are those locations where that changed from an increasing to a decreasing function, so the derivative is 0. Or, if f is not differentiable at c, then c is a critical number. Right? So if you have those locations where we had a jump in the graph, or we have a hole in the graph, we encounter those. We had locations where it had a vertical asymptote that doesn't actually end up giving me a critical value that's going to be max or min because it's a steep part of the graph. But we have those locations where we don't have derivatives. So either locations where the derivatives are 0 or locations where the derivatives do not exist. Those are possible places where we have relative maxes and mins, and we call those values critical numbers. And that's what Theorem 3.2 actually says. These relative extrema, these places where we are under consideration for being the maximum or minimum, are only going to be places where we have a relative maximum or minimum value. And all of those places where we have those relative maximum or minimum values are in fact going to be locations that are called critical numbers. So it's kind of a dual description. Do that picture. Okay, so how do we go about finding these locations? That's actually where we're headed next. Some guidelines for finding extrema on closed intervals. So to find extrema on a continuous function on a closed interval, we find the critical numbers. So what does that really mean? Well, it typically means we take the derivative and we set it equal to 0, and we solve it. Okay, you guys have been through plenty of algebra courses. So this is taking the calculus that we've been working with back in chapter 2 and applying some algebra on the end by setting things equal to 0 and solving. We might end up setting it equal to the denominator equaling 0 or something like that, because those could be locations where we have derivatives that don't exist as well. All right? So we find the critical numbers. Step 2 is that we evaluate the critical numbers. So it means we take, we found out that x is equal to 3, and we plug 3 in, and we say, okay, what is y? Right? We actually find the point, the ordered pair, because it's the y value that is actually telling us if we have our max or min. Let me go back to this picture over here. This location right here is a maximum because it's the biggest y value. I mean, it happens to be at an x value. I mean, there's an x value here, of course, but it's the y value that's actually the biggest. That's what makes it a maximum. Right here is the minimum because it's the y value that makes it the smallest. So we have to ask ourselves, what's the y value that's occurring there before we can make that decision? So when we're looking at evaluating, that's what we're talking about here, is we are actually looking for the y value at that particular location. And we can't forget our endpoints. Typically speaking, students either remember the endpoints or they remember the relative maxes and mins, and they forget the other piece, whichever one it is. There's two things you have to consider: the relative maxes and mins and the endpoints. So we got to do both of them within the consideration. And then we're going to evaluate those endpoints as well. So if the closed interval went from 1 to 10, like I mentioned before, we find out what is f of 1, what is f of 10. Okay, the two y values that correspond. And then whichever one's the smallest is the minimum, and whichever one's the biggest is the maximum. Okay? It's kind of like if I said, if you think you're the shortest person in the room, stand up, and we had all the people who think they're short stand up. So if you think you might be the tallest person in the room, stand up, all the tallest people. And we went to all the shortest people, and we said, okay, now line up in height. Okay, it's you. And we had all the tallest people, we line up in height. Okay, it's you. That's what we're doing when we get to this particular point in the problem. We're taking all of the points that sort of are contenders, and we're deciding which one's the biggest, which one's the smallest. And that's going to be the answer to the problem we're looking for. So we're going to take a look at this particular one. This doesn't ask us to do all the details in the last slide. It just says find the critical numbers. So make sure when you're looking at the directions that you don't do more than you're asked, because none of us like to do that, right? You feel like, I just wasted my time. I did more than they actually asked me to do. Shoot, could have done something else. So this one just wants us to find critical numbers. So what is critical numbers again? Well, it's places where the derivative is equal to 0 or the derivative does not exist. That's what critical numbers are. Derivative equals 0, derivative doesn't exist. And this one's, like I mentioned when we were first starting this lesson, we're going to see much friendlier functions. Much friendlier. You're going to be like, wow. In terms of like taking derivatives, this chapter is way easier than chapter 2. Way easier. So simple rules on this one, in fact, right? Nothing crazy, no products, no quotients, no chains, no nothing. We just need to find the derivative of with simple rules. So what's the derivative of x cubed? 3x squared. And then the derivative of the negative 3x squared? Wonderful. That's the derivative. This is a polynomial. Okay, polynomials are smooth and continuous everywhere. They don't have any places where the derivatives don't exist. None of that happens. So the only piece on this one that I'm looking for is where the derivative is equal to 0. Because the derivative is going to always exist. So I'm going to set this equal to 0. A couple of reminders. If you end up with a linear function, right, you move things around, you set it equal to x equal whatever, and you solve. If you have something that's not linear, you have to factor things. So if it's not linear and it's a rational function, maybe you've got a numerator and denominator you're going to be factoring. On this one, we're going to be factoring a polynomial, all right? So you can't simply move like the 6x to the other side and then divide by pieces. You'll lose values if you try to do that. So we want to make sure that if we have anything that's not just an x and constants in there, that we don't try to do that. So taking a look at this, what common factors do each of these terms have? A 3x, you bet. So if I take out 3x squared, take out 3x, I'm left with x. And if I take a 3x out of negative 6x, I'm left with, negative 2. And then each piece gets set equal to 0 and solved. So x is equal to 0, and x is equal to 2. There are 2 locations where I may have a max and or a min. That's what I just found out. Now, I'm not asked to find the max and min. I'm not asked to evaluate anything any further. That's it. This is critical numbers. Okay? Take derivative, set it equal to 0, and solve. Okay, so example 2 goes a step further. It actually asks us to find those absolute maxes and mins. So we're going to do what we just did on the last problem, the critical numbers, but we're going to continue down the process of evaluating them and checking endpoints as well. So the first thing we want to look at is that we want to look at critical points or critical numbers. Okay? So critical numbers means taking derivatives, setting them equal to 0 or does not exist, and solving. So I'm looking for a derivative equal to 0 or the derivative does not exist. This one doesn't happen because I'm looking at a polynomial. Okay? So what's the derivative of negative x squared plus 3x minus 5? Perfect, negative 2x plus 3. And this is an example of one I mentioned just a moment ago. This is a linear function, right? It's just a line. There's no factoring I need to do on this one. I just set it equal to 0, and I get x alone. So I would have negative 2x equals negative 3. And so x is 3/2. Is everybody good with that? Okay, that's exactly what I did on the last problem. It's a different function, of course, but it's what I did on the last problem. But there's more to it. I need to figure out what's the y value that goes with this. In other words, I need to find f of 3/2. Because eventually I'm going to have to compare all my y values. So if I take this and I plug it into the function original, right? If I plug it into the derivative, I'm going to get 0. That's the whole point of what happened in the last, what I just did, all right? I mean, that doesn't give me any information about the graph itself in terms of the critical values. So what I need is I need to know the y value that corresponds. So if I plugged this into negative x squared plus 3x minus 5, the question is, what y value do I get? Negative 5. Okay, and we'll come back to this in a moment. Okay, so that's critical numbers. The second thing that we have to look at are endpoints. So our two endpoints are negative 2 and positive 1. So there's nothing that I have to do to solve anything. I'm just evaluating them. Okay, I'm just checking out what are the y values there. So I need to do f of negative 2 and f of 1 into my function. So if I plug negative 2 into this function, what do I get? I don't see very many calculators out. You guys are welcome to use your calculator. I don't need you to do it by hand. It's okay. You're like, man, if I have to, I guess I'll get a calculator. It's crazy. Did you get it, Jeffrey?
I think it's negative 3, but that's my head.
Negative 3? I have something written down differently, which negative 15 is what I have written down, so I think that's probably right. There's probably a sign error, and when you did it, it happens. It's okay. How about f of 1? You might be able to do that one in your head pretty quick. 1s are so nice. Almost as nice as 0s. Negative 3? That's what I have. Yeah. Okay. So there are 3 potential sort of answers to the questions that I'm being asked. Absolute extrema, I should have 2 answers, a maximum and a minimum when I'm done. Now there's one caveat to what's going on that I haven't mentioned. Did anybody notice anything weird about this particular, not even that really, but this particular value, 3/2? It is a fraction, that's true. Something else though. Let me graph it. Say that really, say it, and you were about to, somebody else about to say it. Say it.
It's more than 1.
It's more than 1. Why does it matter? Okay, say that really loud for me, Nick. It's outside the interval. The interval that I'm looking at is only supposed to go between negative 2 and 1. Are you with me? So we need to be careful because that will sometimes happen. Sometimes you'll get 2 answers. One of them's inside the interval, another is outside the interval. But the reality is that I only care what happens inside this interval. So this one has automatically sort of lost out as being a contender in the option, right? It's like saying, who's the tallest person in the room? And one of the basketball players across campus says, that's not true. I'm taller than that guy. And you're like, but you weren't in the room. You didn't have a choice. You can't win, right? Like you can't win if you don't play the lottery kind of thing, right? That kind of stuff, right? Like you can't be here, you can't win. So yeah, this one can't even be an answer because it's not in the interval I care about. So the only thing I'm actually looking at are these 2 values. So which one's the maximum? Yeah, the negative 3 feels weird because it's negatives, of course. And which one's the minimum? Of course, the negative 15. So how do we write that? Well, there's a couple of ways to write that. So the way that I've got written down here, which must mean that this is the way that your book focuses on, is to say that we have an absolute max of negative 3 at x equals 1. And we have an absolute min of negative 15 at x equals, I wrote that down wrong, -2. Okay. Okay, so the maximum and the minimum values are the y values. The location where they are occurring is the x values. Is that okay for everybody so far? Okay. Same directions, find the absolute max and min on the closed interval, but this time we're dealing with a rational function. So you have to be careful with rational functions, right? Because rational functions actually do have locations where they're not continuous. When is a rational function not continuous?
The denominator is 0.
Exactly, when the denominator is 0. So the denominator being 0 are locations where we have to be a little bit more careful. So as we're taking a look at this, when we're finding the derivative equal to 0 and the derivative equaling does not exist, we actually have both of those options. It feels a little bit funny to do the derivative does not exist. If it's a rational function, it is in fact going to have an asymptote there. So clearly if there's an asymptote, I don't have a relative maxes or mins. But we're going to keep that in the mix of what we're doing because of an application we're going to be using for this idea later on. Okay? So I realize for the point of what we're actually looking for right now, it's not going to ever be my answer. I get that. But just bear with me while we do it for a couple of lessons and you'll see it come into play. All right, so critical numbers first. Again, it doesn't really matter which order I do it in, but I want to make sure I do both. I need to do critical numbers and I need to do endpoints. So critical numbers means I need to take the derivative, h prime of t. You can do this as a quotient rule if you want. That's totally fine. You can do it as a product rule if you want. If you do it as a product rule, you can take the entire denominator to the power -1. Okay, so I don't care which one you do, but those are just two different options. And you would do it as a product and a chain rule at that point. So I think this one's probably clean enough that a quotient rule is probably the easier option, especially because in the end we want to set it equal to 0 and solve it. So it's going to have less cleanup at the end to do if we do a quotient rule. So can somebody help me and remind me? Quotient rule, what do you do? HODI, denominator, right? T minus 2. What's the derivative of that numerator? 1. Okay, again, this is a quotient rule, but it's way easier than the ones on your gateway, right? It is, and that's going to be consistently doing that in this lesson, or in this section, and the others in chapter 3. And then what about the other direction? I need the numerator, and then what's the derivative of the denominator? It's 1 again. And then I'm going to divide by the denominator squared, so t minus 2 squared. Okay, is everybody good with that? Let's clean up that numerator. So if I clean up that numerator, I have t minus 2 minus t over t minus 2 squared. What does the numerator become?
-2.
-2. And it's over t minus 2 squared. So for critical numbers, I'm supposed to set this equal to 0, and I'm supposed to set this equal to does not exist. So I'm supposed to set this equal to 0 and equal to does not exist. The reality is that this is going to equal 0 when the numerator equals 0. I mean, that's how you get a fraction to be 0, is the top has to be 0, right? And it's going to be does not exist when the denominator equals 0, because dividing by 0 is an undefined operation. So those are the two pieces that we need to consider. I need to consider when h prime of t equals 0, which really means that the numerator equals 0. But what's my numerator here? -2. So when does -2 equal 0? Never. So this doesn't give me any values. There is no location where this derivative equals 0. And I'll draw you a picture as a reminder of sort of kind of the idea of what we're looking at and why that would be the case here. And then the denominator, the second option is when it does not exist. And that's going to be when the denominator equals 0. So that's when t minus 2 squared equals 0. So when will that one equal 0? At 2. Okay. The kicker is, though, that if I try to plug in the 2 in, into the function, I would get a 0 in the denominator, like the original one, right? Not the derivative, but the original one will also give me a 0 in the denominator. So I'd end up with something over 0. So this doesn't give me any values, just like I told you at the beginning it was not going to. Okay. So why is this happening? Well, this is definitely not drawn to scale, but the idea is that when we have rational functions, They look something like this, right? This is just a general rational function, not the one that I'm dealing with specifically. You can see there's an asymptote. That's where that t = 2 is coming into play. You can also see that there's no peaks and valleys, right? Now, there are rational functions with peaks and valleys. This one just doesn't have any because of the way it's structured, all right? Okay, but we haven't done everything yet. We've only done half of the problem. We've done the critical numbers half. What else do we need to do?
Endpoints.
Then endpoints. So number 2, and we need to do endpoints. So the two endpoints here are 3 and 5. So I need to find h of 3 and h of 5. So if I were to plug in 3, what will I get? It is 3. 3 over 1 is 3. And if I plug in 5, what do I get? 5/3. Okay, so which one's the max? Which one's the min?
3 is the max.
Okay, so how do we decide which one's the max or min? Let's pause for a second.
It's the y value.
It's the y value. Yeah, that's why I wanted to pause. You got it. So we want to consider the y values. So if we only consider the y values, the 3 and the 5/3, which of those two is bigger? The 3 is. So the 3 is in fact my max. And then the 5/3 is my minimum. The x values don't decide on those pieces of the information. Yeah. Good catch on everybody's part. Good, good. All right, so we would say that we have an absolute max of 3 at x equals 3. And we have an absolute minimum of 5/3 at x equals 5. Okay, any questions on that? Okay, one more question in this idea. Because no lesson in calculus would be complete without a little trig, right? Now, the cool thing is trig, cosines and sines. They do a lot of this bouncing up and down business, right? Oh, yeah. Peaks and valleys, they're there. Maybe not so much with tangents and that kind of stuff, right? Tangents and cotangents don't have that feature, but sines and cosines do. So as we're taking a look at these, we are fully expecting that we are going to be bouncing up and down a lot, which means that those interval endpoints do really matter. You probably remember back in trig, no matter where and when you took it, at some point they asked you questions like, when does tangent, or cosine, or whatever equal 0? And you had to give answers that looked like, at 3 pi over 2 plus or minus k pi, stuff like that. Do y'all remember that? All right, you don't remember that? Where you had to say it on an interval and you said that it was at this location and this location and this location. It had lots of answers, all right? Depends on the resources and how they're focusing on it. But it really matters whether you're on a closed interval or on the whole number line. And closed intervals are a lot easier to work with because we have an isolated number of answers. So we're taking a look at this one. We are on the interval 0 to 2 pi, so one full rotation of our unit circle, right? Okay, so all the rules are still the same. Critical numbers, endpoints, all that's good. So we're first going to look at critical numbers. Also probably worth mentioning here, so the derivative equaling 0 and the derivative not existing. For cosine, the derivative doesn't not exist because it's nice and smooth, right? The sinusoidal curve. Right? Sines and cosines have this nice smooth feature. So I don't have this here. If I were dealing with tangent or secant or cosecant or cotangent, I would have that happening, all right? And interestingly enough, we have some really odd things happen with some of those kinds of functions. Most of the ones we like to deal with when we're talking about this are the sines and cosines, though, so you'll see those much more frequently. So really, it's the derivative equaling to 0 on this one that's going to matter. So what's the derivative of 3 cosine x? Negative 3 sine of x. You got it. And I want to know where the negative 3 sine of x equals 0. Well, the reality is the negative 3 is irrelevant, right? If you'll remember from trig, what that -3 really does is it like flips graphs upside down because it's negative, and it changes amplitude, how steep and shallow it goes, right? So how far away from your x-axis. But it doesn't change where it hits the x-axis, right? Those x-intercepts don't change. So this is equivalent to saying the sine of x equals 0. Another way to think of that more from an algebra perspective is I can divide both sides by -3 and it doesn't change. So now you got to put on that trig hat. Because sine equals 0 in more than one place, and if you try to use your calculator, it will only give you one of them. Because your calculator can only give you one answer. So like if you try to do this in your calculator, the inverse sine, it will give you an answer, but it's only going to give you one. And you've got to figure out what the other one would be. So the unit circle is a good place and way to figure that out. Does anyone remember from their unit circle, where is sine equal to 0? 0 and pi, and actually 2 pi as well. Now, in this case, it's very interesting because 2 of those are the endpoints we're looking at anyway. So we almost get the endpoints for free on this problem because they're part of the first part of the problem. So we won't actually end up, I'll write it down, but we won't actually end up doing any additional work for endpoints here. So we have 3 locations for possible maxes and mins. And if you think about it, it kind of makes sense, right? So this is what sines and cosines do. They hit a max, and then they go down and they hit a min. And they come back up and they hit a max, and they go down and they hit a min. So this repeating process makes sense. And it should be expected as well that you're going to have 2 answers for either the max or the min answer. I don't know which one yet. We haven't done it. But one of these answers, 0 and pi and 2 pi, is going to be a minimum, and the other one is going to be a maximum, and the third point is going to be a repeat of the other one. Okay, so let's take a look at it, and I'll show you what that looks like. So what is our function called? G. So we're going to do g of 0, g of pi, and g of 2 pi into the original function g right up here. So 3 cosine of x with 0 in, with pi in, and with 2 pi in. So if you plug in 0, what do you get? What do you get? 3. If you plug in pi, what do you get? -3. And if you plug in 2 pi, what do you get? 3. Right? It's bouncing up and down. That's what it does. Again, this shouldn't be any surprise that you're getting 3s. It's the amplitude. I mean, that's exactly what happened. It stretched the graph up and it stretched the graph down. If this equation had something like a +5 at the end or something, of course, that would shift it all, the entire graph up and down, so it wouldn't necessarily hit the peaks and valleys of the same number because it has a vertical shift. But this one didn't. All right, so looking at these points, actually, let me just make a comment here since I said I would. If I were to look at endpoints, they wouldn't have to coincide, but they do, right? It's g of 0, g of 2 pi, and we've already found them. G of 0 is 3, and g of 2 pi is also 3. Okay, so we don't end up with new information, but they're there to remind us that we do have to check them. Which one is our max? What is our maximum value? 3, right? This is the max. But the kicker is it happens twice, of course, right? And if we extended the interval, it happened even more than that. And the -3 would be our minimum. So what would we answer? Well, we would say that we have a maximum of 3, and it's happening at x equals 0 and 2 pi, 2 answers, and we have a minimum of -3 at x equal to pi. Who's excited about derivatives that are cleaner to work with? Me too. It's lots easier to grade, just FYI. Yeah. Lots easier to work with. The algebra at the end is the new part of what's really going on here, okay? Any questions on that? Awesome. All right, so next time what we are going to encounter is something called Raleigh's theorem, and I think the mean value theorem maybe as well. And we're going to talk more about the relative maximum and minimum values and some pieces of information about that.